It is a great pleasure to be here, and it's a wonderful, wonderful thing that EMI is organizing this community of practice to come together. So we get to know each other, ask questions, be candid and frank, and build our community, okay? Much like every other community, we need support and candid disagreements too. So I'm going to talk as an exemplar about stopping arsenic poisoning in India and the lessons learned. But it's not so much about, as you'll see, the talk is not so much about the technical content of it, because you guys can come up to speed very quickly. The next slide, please. All right. So with grateful thanks to everybody who funded this, because it's more than a couple of hundred individuals and about 24 organizations. I'm very grateful to them for the support and for the individuals for their generous advice and contributions. The next slide, please. There was this massive installation of hand pumps in Bangladesh and India as a way to fight diarrheal disease in the 80s, and 10 million hand pumps, shallow tube wells and hand pumps on them, were installed in Bangladesh alone. And arsenicosis appeared in the population in early 1990s. It seemed that some engineers in the British Geological Survey had spotted arsenic in the groundwater, but it didn't get reported, or nobody cared that much about it. People said, let's just push on. So this is what happened. Lots of people in the right-hand side of the picture are showing their hands or their palms, because arsenicosis shows up as hyperkeratosis, those black thick spots, even on that little girl's hands, and then all those women's hands. And then a lot of people develop gangrenes and ulcers, and then they lose their hands or fingers and thumbs, and eventually they die of cancer. Next slide, please. So access to safe drinking water is a basic fundamental human right, according to the UN resolution in 2010. Is also a prominent sustainable development goal number 6. Close to 100 million Indians have no other water to drink than groundwater with toxic levels of arsenic. And of course, Bangladesh is a horrible hotspot for arsenic in groundwater. And even though arsenic is ubiquitous on the Earth's crust, the threat of arsenic is unevenly distributed. And that's why, fortunately, there are only about 200 million people worldwide, maybe 250. The next slide, please. As I already mentioned, chronic exposure has horrible effects. In the year 2000, WHO called it the largest mass poisoning in recorded history. But on the ground, there is very little progress, even today. Next slide, please. So how bad is arsenic? Okay, let's examine only internal cancers, which is one of the outcomes of arsenic, not the amputations and not the neuropathy and not the child's intelligence retardation. The predictive models, which are very good quality, based on high quality data on arsenic and cancers. And we ask the question, how many excess above the baseline internal cancers can be expected in 100,000 people over a lifetime consumption of a carcinogen bearing water at its allowed maximum concentration level, at its MCL. Next slide, please. Now you see in this graph, on the graph is titled Lifetime Cancer Risk from various carcinogens at their MCL. Some carcinogens are allowed, and they are all listed here. And the excess cancer risk is now on the vertical axis, on the y-axis. In this graph, they're rank ordered. The worst one is ethylene dibromide. which produces about 12.5 excess cancers in 100,000 people over a lifetime of consumption. Arsenic is not shown, is missing. The next slide, please, shows the arsenic. Note that the vertical axis has changed. Now, red column is arsenic at its MCL, 10 parts per billion. And the previous graph is now barely visible. Previous columns are barely visible. And that cancer risk is horrific. It's already 0.7 per 100, okay, or 700 per 100,000. Next slide. That risk was at 10 parts per billion at the MCL in WHO or US EPA. Australia has a lower one. Netherlands has a lower one than 10. And we found arsenic concentrations which are many, many, many times higher. And the risk rises linearly with the concentration at these values. Next slide. This figure shows 12 photographs taken by a then PhD student in 2012, Abhijit Das, who was studying how long do arsenic remediation units last once they are installed. So there are photographs of arsenic remediation units called ARUs in one of the worst hit districts, Murshidabad district. And the ARUs, as the text says, are based on sound technologies that work in the lab, and they are expected to work in the field. Okay, the next slide. Abhijit's research showed that more than 95% of them failed within 1 year. And that's because what we need really is a sustainable technology system, which is not just effective and robust, but also financially viable, locally affordable, scalable, and socially embedded. You need a lot more than something that works in a lab, in other words. The next slide. So what went wrong? The technologies, I wouldn't say technologies had failed, okay? The technologists had failed and their institutions had failed because all they did was check a box saying system installed. But the systems were unsustainable. They were financially non-viable. So when there were columns of adsorbents, the adsorbents were too expensive to replace. And there was no mechanism to collect money suddenly at the end of 2 years or 1 year or 6 months to go and replace them. So nobody was collecting any money. It was a donation. They were detached from the societal context. Nobody knew what this thing was. There was no incentives or structures or mechanisms for maintenance and repair. There was no knowledge transfer to the local community. Nobody was invested locally in having that darn thing there and keep it functioning. Next slide, please. So ECAR, which stands for Electrochemical Arsenic Remediation, was designed to fit within a sustainable and scalable technology system. And this is the only slide I'm going to describe about how it works. How does it work? You have two steel plates in the water with a DC current at a low voltage, about 10 volts. The anode dissolves, produces Fe2 in the water, which reacts with oxygen and turns into Fe3, which is hydrated. In that process, all of the arsenic 3 is turned into arsenic 5. That attaches to the HFO, or hydrated ferric oxyhydroxide, settles to the bottom as a sludge, and you remove the sludge and clean water comes out. And this is one of those pie in the sky unattainable things for most environmental engineers called ZLD, which stands for zero liquid discharge, which means that you take out the toxic stuff from the water only as solids, leaving in principle every water molecule that came in to the raw water leaves out as a good water. Okay. Next slide, please. So back in 2005, we started working. 2006 is a picture with Susan Ambrose, in fact, in there, looking at a 200 milliliter little device. And in Amirabad High School in 2010, it had graduated to the point, at that time she was a postdoc. We had a 100-liter device. You see that white tank there. Okay. The next slide shows our 600-liter device in 2012, which we placed in a school in Davdapi 2013. That's the middle picture. And after that tested well, we scaled it up in 2016 to a 2,800 liter reactors of 1,400 each, 2 tanks. Okay. So it took time to scale up and grow. In parallel, we did our science carefully, engineering carefully. Here is a team of lots of people. In 2016, all of them are local people in India. Some of them are faculty, some of them are students, some of them are staff. The girl sitting in the center wearing the blue dress is a PhD student now finishing up her PhD in my lab at Berkeley. The cost of consumables is 1/20th of a cent per liter to remove 250 ppb water all the way down to 3 ppb. And that's part of our design smarts. Okay, it delivers 10,000 liters per day. And here is the performance of the plant. Inlet water is 252 or 250 ppb. Outlet water average is 2.9 ppb, far below the 10 target, which is shown as a blue horizontal line. Right? Go to the next slide, please. In fall of 2016, students and staff get electronic cards, which are like on the electronic kiosk. It's a dispensing card with which they pick up 1 liter of water every day, free, in exchange for the school giving us a classroom to build all this. We had promised the school that if it works, this is the way we'll operate. If it doesn't work, we'll pack up everything, leave the schoolroom clean and neat, back in the same shape or better than when they gave it to us for 2 years of experiments. On January 31, we handed the whole thing off to a private sector company who were our partners all along. Now they manage, maintain, operate the plant, make a decent profit out of it. They pay salaries of 2 local workers, and the plant continues with free water to the school, 2,500 students, 400 teachers and staff, and the excess water is sold to the community, and that is where the money comes in. So what is the impact of ECAR on the lifetime cancer risk? At 250 ppb, the orange bar, is 18,000 excess cancers per 100,000 people over a lifetime. When we reduce that all the way down to 3 ppb, it's an 80-fold reduction in the cancers. Now lifetime risk is 0.21 per 100, is well below the 0.7 per 100, which happens at 10 ppb. And the water is locally affordable. As I said, it's sold at 1 cent per liter. And that is, remember, the cost of supplies, consumables, is 1/20th of a cent. But this includes salaries. Okay? And salaries are a big chunk of the total cost. And so it includes also the 2 employees, but there is a whole structure of collecting the cash and replacing the supplies and management and overheads and the business margin of the company. Next slide, please. So the designing for user experience was about the electronic cards and the electronic kiosk, where you simply hold up the electronic card near the dispensing machine, and this girl on the top left is proudly showing her personal card with her name and grade level and a roll number. But that way, the company also is able to collect the data of who collects the water and how much often they collect the water, and do they come twice for half liters or whatever. So that's part of the monitoring as well. Next slide, please. Now we come to how things oftentimes fail. Okay, the top bar is stages of technological maturity. It goes from ideas on the left all the way to scale up on the right. The vertical columns are the cash flow. It becomes more and more and more negative until you go to the large prototype, where is the largest negative, and the cash flow is on the logarithmic scale. Okay, so you can estimate the IBM numbers. Actually, in their manual or in their guide, they say that the large prototypes, which are full scale, will cost about 10 times more than the cost of development. And then, of course, you are into commercial and scale up. In our case, we have a demonstration project, which was actually a field test that turned into a demonstration, if successful, and we left it with the company to commercialize. This is the key lesson learned given the limited time. I'm just jumping to tell you what is a core here. The core is that there are 4 strategies that are interlocking. The first word on the slide is very important. If we design a technology for a community scale, we are able to collect the money on a pay-as-you-go scheme. But a pay-as-you-go scheme means that it has got to be affordable, which means you got to think all the way at the beginning of your design. But not only that, people won't come, or you won't be able to pay the local employee if people don't come. So the second step is increasing the economic opportunity, depends on pay as you go, and pay as you go depends on making things affordable. But even there, people coming to pay as you go, even if it were affordable, it won't happen if they don't know what you're doing and why. So you have to bridge the knowledge gap, the knowledge divide, and make them understand, take them with you on the journey about why is arsenic there in the water, how you are there to help them remove it, how the water is still theirs, but removing arsenic is going to cost money and they have to cover that tiny cost of removing arsenic. And then, of course, to do all that requires a business model. And for the business to work, you need to get all the permissions and all compliance from all the local regulations. There are environmental regulations for disposal of waste, for example, and there are business rules and business permits. You got to go through all of those. We did all that, okay? So now I jump to our current work, a couple of slides on the current work. Since this plant has been running since 2016 just fine. Even under COVID, it has been running. The next work that we focused on was how to make things faster. We call this new technology ACAIE because it's simply the acronym of Air-diffusion Cathode Assisted Iron Electrocoagulation. It so happens that ACAIE is also the name of a Brazilian berry, apparently. And it's a drink you can buy in Brazil. If some of you are from Brazil or have been there, you might know that. We make an air diffusion cathode so that it is a porous membrane exposed to atmospheric air. Oxygen comes in, reacts with the electrons that are dumped into the cathode and turns it into H2O2. Now H2O2 reacts with Fe2 10,000 times, about 10,000 times faster than dissolved oxygen. Otherwise, it's the same chemistry. So the Faradaic efficiency of H2O2 production is huge, 80%. dissolved oxygen is not depleted in the whole process, and the whole thing moves a lot faster. How fast? Next slide. I want to draw your attention to the horizontal green bars. On the right-hand side is ACAIE, and we can remove, according to the orange box on the top, about 1500 ppm initial arsenic to less than 4 ppm, or ppb, sorry, less than 4 ppb final arsenic. We can do that in 30 seconds. On the left-hand side is the same reaction, same reactor, same size, same coulombic dose, 600 coulombs per liter. To make that happen in ECAR takes 3 hours and 20 minutes. So 3 hours and 20 minutes is what we installed, that low-speed technology in India. But now we can do it in 30 seconds. Next slide, please. So we are now funded by the state of California to demonstrate this on a 600 liter per hour LPH, 600 liters per hour scale in Central Valley of California, where we have arsenic in groundwater throughout up and down the Central Valley. We have 132 ppb arsenic at a field site in Central Valley on task 1, which we reduced to 3 ppb. Very good, very fast. Now the task 2, we are stalled because of the COVID. But the idea is we build those 60 LPH ACAIE modules. We're going to stack 10 of those, and we are going to get 600 LPH. And we'll get there once the COVID restrictions in field research are relaxed. That's where I want to stop, and I'll be happy to take questions. Thank you so much. You have my website there, you have my email address there, but most importantly, I want to be able to speak with you and answer questions to the extent we can. Thank you again.
All right, great. Thanks a lot, Ashok. I think that was a great picture of what a real project looks like. From initial kind of problem definition through testing it out in the lab to taking it to the field. So that was a really great picture. And so people can you can type your questions into that chat, and I'll pass them on to Ashok. We'll take about 10 minutes or so here for questions. I know that we're a little bit late, and then we'll move over to the networking for the last 20 minutes. So I have one here for myself, is that these types of projects are really long. They're long-term projects. You showed from even in your own planning. I think you started in the 2000s and you finished up with a kind of a scaled field demonstration in 2016. So it takes a long time. So when you're thinking about these projects, how do you work through the whole trade-off? Thinking about when do you bring how do you work with your end users through that process when it's when you have a lot of first R&D that needs to happen, and how do you make sure it's going to be something that's going to work with those end users even after you go through that long process?
No, it's a very good question. I don't want to ever risk wasting money on lab research, money and time on lab research, and then discovering, oops, I solved the wrong problem, right? That's not good engineering. So customer discovery and lab research happen in parallel. They happen at different levels of depth. So at the very beginning, I need to understand what kind of people am I working with? What is their ability to do this economically? Or is it always going to be somebody's charity? Or are there some vast pools of funding available which will always support it, and I don't have to worry about the money part, right? So all these aspects I have to bear in mind even when I take a given approach. So back in the year 2000, I didn't show this. I took an approach of coating microscopic particles of silica and silicate, spherical particles with ferric hydroxide. and using them as a dispersed medium in water, and they capture arsenic 3 and 5 both quite well. Because I was thinking for a large surface area, low cost adsorbent. But then I discovered that to make this on a large scale is the only way to make it affordable. And that caused me to back off when I discovered ECAR in 2005, and I abandoned the line of research from 2000 to 2005. Okay, so it is a risky thing. As always, research is risky, man. Come on, right? But you don't make fatal mistakes. You make mistakes, but you survive. That's fine. And then there is no looking back, because then I had a much better grip of what is needed. But even we did not go and actually transfer things to the field until 2010. We went to the field, we understood the customer, but only through talking to people. First field trials by going to a scaled up device was 100-liter device that we made in 2010. And every time there was a learning curve of trying to understand, does it work for these people? Does it work for these people? And so on. I hope that answers your question. It's a parallel process, right? Yeah. There is actually a slide which doesn't show, because maybe I sent you the wrong slide deck, which shows the work we did for community outreach from 2010 onwards up to 2016. There was intense work to just meetings with every single stakeholder who was both local from the government side, school administration, school teachers and students, and school community. All of that outreach was very, very important.
Great. So a question just popped up here. So this is a question from Ahmed Mahmoud. So how do you convince donors that research, which is risky and often difficult to scale, is better social investment than tried and true infrastructure?
It is not an easy sell, particularly in the developing world, where oftentimes research is not part of the culture. Even in India, even in West Bengal, where 100 million people are now in India overall, exposed, the standard, what can I say, mindset of the public water agencies is to figure out some place where there's surface water and lay long pipes, okay? And they're unable to do that because arsenic is a distributed problem. And you can't lay pipes to bring surface water to distributed villages, which is over tens of thousands of square miles. You just can't do it. Same thing has happened in central India, where we have fluoride problem. From about 1960, those villagers have been promised safe drinking water. Every election cycle, they say, yeah, we're going to lay a new pipeline for your village. And now it is 2020, okay? There's no pipeline. These guys are just poisoning their children, primarily because they get deformed with a fluoride in the water, and have no way to remove fluoride from their groundwater. No way. It's god-awful to see that.
Yeah, I think it's definitely a balancing act. And I think part of it, also in these types of projects where when you're looking at developing a new technology,
it's also a new approach. It's also a new approach. Mm-hmm. And a new approach is not to always rely on the trusted politicians to deliver what they promised during election time, point one. Point two, figure out a way if something can be done in a financially viable way without depending on government handout. So my another invention called UV Waterworks, same mindset, saying government is not going to do it, man. They will promise it. That's good for them to get a vote. But Indian villagers need safe drinking water, and they cannot afford to boil it, because boiling your drinking water takes 3 times more fuel than the fuel you use to cook your food, and there is not enough fuel going around. So figure out a way to make it work in a way that is financially viable for a startup. So there is a startup called Water Health International, waterhealth.com. You can go to their website. They license the technology from the university and now serve safe drinking water, sell it for profit for about 25 million people around the developing world, primarily in India. So there's no handout. I can't, I wish there was handout. I'm not opposed to it. But I think the time scale of persuading a government engineer or a politician to change the mindset of how they work, I'm impatient. I don't think I want to do it. Somebody else can do it. Good luck to them.
Yeah. So I think we probably have time for one more question. I saw one just pop up here. It's more about thinking about the barriers. So Monisha's asking, what are the barriers in partnering with communities in need of safe drinking water, specifically in the US and Canada? And then I'm going to also just tag on another thing. It's like, so thinking also in the global development context. And then maybe if you can also comment on some of the ethical considerations, you have to go through when you're doing that kind of work as well.
Sure. So I think I tell my students, I tell myself, and this has been a good guide for all my work in global engineering, is two things are non-negotiable in my research. Absolutely non-negotiable. One of them is I must always keep the interest of the community in mind. I must never, ever harm the interest of the community. If I'm trying to solve a problem in a community that trusts me in a particular way, and a cheaper, better, faster solution gets known to me, I must present that solution, not something that I cooked in my lab, okay? Because I got to be true to the interests of the community, not interests of promoting my research onto the community when there is a better solution in somebody else's back pocket. So I'm showing you important ethical issues here. One of the two is being true rigorously and candidly to the interests of the community when you know that you have some uncertainty about your scientific result. You have to say, we are not sure. We are working on it. Okay? How low can you get the arsenic? I know I can get it down to 1 ppb. Now I know that. But at that time, I said, we can get it down to 5 ppb or 10 ppb in the lab, but oftentimes things perform worse in the field than they perform in the lab. So if it doesn't work, I promise that with my funds, I will take everything down and send it to the junkyard and give your classroom back to you. And thank you for letting us do the experiment in your lab, okay? Be upfront and they wouldn't kick you out. Be honest and they would appreciate it, saying you're telling it like it is. So these are the kind of things where I don't want to tell them a story because they don't know how to measure arsenic at a ppb level, right? So the many ways there, but that's the first part of the two-part solution. The second part is always be rigorously true to the science. If you find that something didn't work, just say, sorry, it didn't work. That's how research is. We'll come back and try to fix it. If it doesn't work, we'll pack up and go away and thank you, right? But never allow the press, the photographers, the prizes and the awards and the publicity get the better of science. Science is a fantastically impressive way to do work and advance anything, but at the same time, science is just there. It's not like a press or a photographer or a prize money, right? So that can be very seductive. And in many ways, things work when the photographers are there or the journalists are there, and they fail when the journalists leave. That's a common criticism of people who go out and do things with communities of poor people, because poor people don't have political power. They don't have a voice. They don't even speak English like your journalist friend does. Okay? So be very rigorous about the science and things that work.